Hi there. Welcome to lecture 24 of Machine Learning from Data. And we're going to continue talking about this optimal hyperplane, this fattest hyperplane that fits the data, that's most robust to measurement error. In particular, we'd like to discuss, why is this fattest hyperplane the best? Is it just intuitive, or can we put some meat into that statement? And once we have handled this issue, then we made this assumption that the data is separable, so we'll have to discuss, what to do when the data is not separable. Now, quick recap of what we did last time. So we introduced this concept of the optimal or the fattest hyperplane. And here's a toy example with 4 data points, two red X's, 2 blue O's. Okay, and this fattest hyperplane has a maximum width, a maximum margin, and that's illustrated in yellow. Okay, and we showed how to solve this specific problem by hand. Okay, and when we talk about can we efficiently find this, fattest separator, we reduce the problem to quadratic programming. Okay, so specifically, the algorithm in what's called the primal form is to minimize the norm of the weights. Now remember that we separated out the bias, so we are minimizing only the norm of the feature weights, minimize the norm of the feature weights, subject to the constraint that you separate all the data. And we discussed this notion of separation where y times w transpose xn plus b should be greater equal to 1. So without loss of generality, that's what it means to separate the data. And, when we do this, we find that, basically what's happening is you put this separator and then you increase the margin as much as you can, and the optimal separator increases the margin, to the largest possible width. And when you've obtained this optimal separator, as you're increasing the margin, as you're increasing this cushion, you will simultaneously hit a red point and a blue point, so a point on each side an equal distance away, and then you've got the width of this optimal separator. Okay. And then when this happens, there'll be some points on the cushion that are right on the cushion, illustrated here with boxed red X and blue circle points. Okay, these we call support vectors, and the interesting observations are the support vectors seem to be the important data points, but even more interesting is that if I throw away this other data point, or all data points other than the support vectors, basically the optimal separating hyperplane doesn't change in any way, and its width doesn't change, and its position is not going to change. So all you need are the support vectors in order to sort of recover this fattest optimal hyperplane. Okay, so that's the algorithm. It's quadratic programming. Mathematicians know how to solve this problem. Okay. And I showed some examples on, actually this is a toy data set where you have a target function, you generate red X and blue circles, and here's the optimal separating hyperplane with its width. The gray lines are the sort of thickness, the cushion, okay, and the support vectors are boxed, okay, and its out of sample error is some fixed value. Now, if you run the PLA, depending on the order of the points and depending on which point you pick as your misclassified point for each PLA update, you end up at a separating hyperplane which could be quite variable, and so you get a distribution of out of sample errors. Some of them can be better than the support vector machine. Some of them can be better. If you're lucky, you get a better. If you're unlucky, you could be much worse. Okay, the support vector machine is nice, deterministic, and has this nice property that it's as fat as you can get, which means that it tolerates the maximum amount of measurement nodes. So today, let's start by trying to address, is fatter better than thick? So that's what we're going to address. We started this a little bit last time by building this link between the fattest hyperplane and regularization. So, when all is said and done and we look at the algorithm for obtaining the optimal hyperplane, we minimize the norm of the weights. So we minimize the norm of the weights, subject to fitting the data. That's sort of what Occam said. Subject to explaining the data, get the simplest hypothesis. It's literally Occam. Okay? And that's what the optimal hyperplane is implementing. Okay, when we studied regularization, we were minimizing the in-sample error subject to a budget on the weights, subject to a budget on their complexity. So in some sense, you can view this optimal hyperplane as maximally regularized, providing that you can explain the data. Okay, and now and later today we'll discuss what happens when the data is not explainable, okay, and how do we sort of extend this algorithm to the situation where you cannot find a linear separator. Okay. So in some sense you can view this optimal hyperplane as performing automatic regularization, automatic maximum possible regularization, providing that you require me to fit the data. Okay, so we're going to start by addressing the question of is the fattest hyperplane better? In other words, is it generally speaking better to separate the data with a large margin than with a small margin? Okay, so we'll provide 3 justifications of this. The first is just experimental. We'll run an experiment where we, pick a separator and we see what happens if on average when the separator has a large margin or when the separator has a small margin. And I'll show, results for E out and results for the bias and variance. And that'll be pretty convincing on its own that, yes, larger margin seems to be better. Okay. Then what we will do is we'll show that indeed you can take fat separators, okay, compared to thin separators, and you can show that the VC dimension can be bounded by something that can be smaller than d plus 1. So d plus 1 is the VC dimension of the perceptron model, which corresponds to the thinnest possible separators. Okay. We can show that fat separators can have a smaller VC dimension than thin separators, which then means that the link from E in to E out is better. Okay. So that's a little bit of theoretical evidence for why fat or large margin separators are better. And finally, we will do something that's quite interesting, okay, and it's going to have an impact on what we discuss later, which is that we will get a bound on the cross-validation error for the optimal hyperplane. That's going to be a very interesting bound. Okay. It's going to be a bound on the cross-validation error that does not explicitly depend on the dimension of the space. That's going to be very interesting. Now remember what the cross-validation error was. You leave out a data point, you build your model, and then you classify the left-out data point, and on average, what's the error that you make on the left-out data point? So the cross-validation error is an estimate of the out-of-sample error that you expect to make, or it's an unbiased estimate of your expected out-of-sample error when you learn on n-1 data points. So at a high level, the cross-validation error is an estimate of your out-of-sample error. And we will show that for this optimal hyperplane, the out-of-sample error, it turns out, does not depend explicitly on the dimension. You can get a bound for the cross-validation error that is dependent only on the number of support vectors. Remember what those support vectors were? They were the points that are on the margin, okay, that lie on the margin, that prevent it from expanding more, the important data points. So, 3 pieces of evidence that allow us to get a handle on the sort of generalization and overfitting or better regularization capability of the optimal hyperplane, this fattest hyperplane. Okay. So let's begin with some experimental evidence. Let's start with some experimental evidence that suggests the fat hyperplane is better than the thin hyperplane. And the result of an experiment is shown on the right. Let me briefly describe the experiment. Okay. So here's the idea. Generate a separable data set. Generate a separable data set. And we used n equals 20. So now, this is not, a proof that fat hyperplanes are better than thin hyperplanes. This is just some experimental evidence. So most of the details are not that important. So, follow the gist. Okay. The second step is, okay, now that we've generated a separable data set, generate, so that there'll be many possible separating hyperplanes, randomly generate 50,000. So that's what the experiment that we ran. Randomly, and I'll put this in quotes. There's a question of what does randomly generate a separating hyperplane mean? Does it mean it's separating with varying shift? Can you also alter the angle and so on? But the details are not so important. The idea is what's important. So randomly generate 50,000 separating hyperplanes. Okay, so I have some separable data. I randomly generate 50,000 separating hyperplanes. And for each such hyperplane, okay, so I have hyperplanes H1, H2, up to H50,000, 50K. Okay, so each such hyperplane has a fatness, the distance to the closest data point. So let me call that, gamma of H1. I can compute gamma of H2 and so on, up to gamma of H50K. And now, once I've generated this data, I can compute the fattest possible separating hyperplane. We call that the margin of the data. So, and I can compute the ratio, the ratio between the fatness of the random hyperplane and the fattest possible, the optimal. So let's call this gamma of H1 divided by gamma opt, divided by gamma opt, divided by gamma opt. Let me call this rho 1, rho 2, up to rho 50K. Okay, so this is basically what fraction of the margin available, what fraction of the width available did your random hyperplane capture. Okay, and for each hyperplane, since it's a simulated setting, I can compute E out. Okay, I can also compute E out of H1, E out of H2 da E out of H50K. Okay, so now I have the fraction of the margin captured and the out of sample error. When the fraction of the margin captured is 0, that means that the random hyperplane is basically sitting very close to one of the data points. So its width is close to 0. When the fraction of the margin captured is close to 1, it means it's nearly optimal, nearly the fattest possible separating hyperplane. Why am I normalizing by the maximum available margin? Is because I'm now going to repeat this many times. So repeat by generating many data sets. And so by comparing the margin you captured with respect to the maximum available margin, that sort of, puts each data set on an equal footing. We're viewing each data set through the lens of what's the maximum available margin. Okay, so the margin captured by a random hyperplane as a fraction of the available margin, we can plot on the x-axis. Let's call that rho, goes from 0 to 1. And on the y-axis, I will plot the average, out of sample error among those hyperplanes which captured that amount of margin. So E out of rho. Okay. And, the optimal hyperplane, we can call this the support vector machine, attains a certain value of E out. Okay. And the typical, and so versus rho, we can look at what the out of sample error is, and that's what that plot on the right shows. Okay, so it's real data. We really did this experiment. And what we see is that if the random hyperplane captures a small margin, its out of sample error tends to be large, and as it captures a larger and larger margin, its out of sample error tends to drop. Okay, and something interesting happens at the end here, where it turns out that, it continues to drop as you capture a larger and larger margin, but then it starts going up a little bit, at which point, you get to the out of sample error for margin equals 1. That's the optimal hyperplane. Okay. This is interesting, and, this is sort of suggesting that, going purely for the maximum margin is not completely the best thing to do, but it clearly shows that bigger margin is better. We may conjecture what's going on here. Basically what's happening is the optimal margin just looks at these few support vectors, these few data points that define the fattest separating hyperplane. And what this is suggesting is that those other points might also be able to contribute to lowering the out of sample error. Okay, which means that if you want those other points to contribute, you have to pay some attention to them, not just the support vectors, and that will result in a slightly, thinner hyperplane that pays attention to some of the other data points. Okay, so it's a little bit interesting when you get to close to 1, margin, close to maximum margin, but there's clear evidence that larger the margin, the better the out of sample error. Okay? So fatter margin is better with respect to learning, with respect to what we care about. And we knew that from the intuition. It's more robust to measurement errors. Okay. Let's look at another experiment. So there's no harm done in looking at experimental data to justify intuition and theory. You should always do this. Let's look at the optimal hyperplane from the perspective of bias and variance. Okay. And I'm doing a simple experiment. So again, just to show you some evidence for how the fatness of the hyperplane, or how the fattest hyperplane is helping us. Okay. So here's a simple experiment. I simulate a simple learning problem in which I have a flat target function, and on top it's +1 and the bottom it's -1. So here's +1, I generate a few data points. Okay, and the bottom is -1, so I generate a few data points. Okay. Now, I'm going to try to separate this data again with flat hyperplane. So that's my hypothesis set. And what we're interested in is the margin of this hyperplane. Okay, and the fattest hyperplane is obtained by picking the flat separator that sort of bisects the distance between, the vertical distance between the lowest blue point and the highest red point. So that might be something like, this hyperplane, this flat line here, plus above, minus below. And so this is its margin, or this is its cushion. Okay, and that's the width. Okay. Now, if I'm generating a random hyperplane that separates, that random hyperplane can be anywhere, between this blue and this red. So anywhere, any flat line between this blue and this red, the optimal fattest hyperplane is always going to be this one. Okay, now I generate random data points, random data sets. I generate many of these data sets, and I can look at, where is the optimal hyperplane and where is the random one. The random one will play around in this region. And as the data set changes, that region can either get larger or it can get smaller. Okay, and what's shown in the bottom left, okay, is, where is that optimal hyperplane? And on the right we show the frequency that the optimal hyperplane is at that point, and where is the random hyperplane? So in blue is the optimal hyperplane. Okay, and so if this is 0, so this is 0 where the target function is. Both random and optimal are symmetric around 0 because it's equally likely that your data points are more skewed towards the bottom or the top, and that will generate separating hyperplanes skewed towards the bottom or the top. Okay, so the optimal hyperplane is most likely to be close to 0, so this is 0, and then it's dropping. Okay. It's very rapidly dropping. Okay, beautiful. Okay, so that's the optimal hyperplane. Maybe it's a little bit taller here. No. Something like this. It drops pretty rapidly. What's happening with the random hyperplane? So the random hyperplane, again, the most likely random hyperplanes that you get are concentrated around 0, but they're slightly lower probability than optimal, so they're something like this. Okay, but the distribution is a little bit fatter. Okay, it goes a little bit wider. And that's because, it's a random hyperplane, so it plays around a little bit with that extra, width that's available to generate a random hyperplane. So it looks more like that. So what do we observe? On average, both of them give close to the target function. So their biases are going to be comparable. But look at the variance of the random hyperplane. And no surprise, the optimal hyperplane is this deterministic bisector of the, lowest blue and highest red, vertical distance. But the random one has variance. Okay? And that's shown in where the hyperplane ends up, separating the data from. Okay? And so we expect that the optimal hyperplane will have a comparable bias and much smaller variance. And indeed, you can see in the table there. Okay, indeed, actually, the bias of the optimal hyperplane is slightly lower, okay, but the variance is much lower. And then remember, for classification or regression, squared error, the out-of-sample error is the sum, bias plus variance. So the optimal hyperplane wins. It wins mostly because it lowers the variance a lot. Now, let's think back to regularization. How did regularization work? Regularization was constraining the hypothesis set, constraining the fitting of the data, okay, and in doing so, it considerably reduces your ability to overfit to the noise, considerably reducing your variance, and hopefully the side effect, the bias, wasn't getting too much worse. Okay, so that's how regularization worked. Well, the optimal hyperplane significantly reduces variance, okay, and even can improve the bias. So it's even slightly better than the standard weight decay regularization. Okay. Doesn't really hurt the bias, not much side effect at all, but shrinks the variance. So there's no reason not to use it. Okay. And indeed, okay, we already sort of had a sort of idea that the way that the optimal hyperplane is helping us is by allowing us to tolerate noise, i.e. becoming robust to noise, i.e. that's what regularization did. And now we see it even in the bias variance analysis. And it has the same effect in some sense as regularization. Okay. Let me now show you that the VC dimension of the optimal hyperplane, the fattest hyperplane, can be smaller than the VC dimension of thin hyperplanes. Now this is getting more towards a theoretical justification of the fattest hyperplane, which will then mean that if its VC dimension is smaller, the link from E in to E out is going to be better. Okay. So let's erase this. Let's consider the points, the pictures on the top there. Okay, so I'm showing in 2 dimensions 3 data points. Okay, and in particular, I'm showing 4 dichotomies on these 3 data points, and the perceptron can separate all 4. In fact, we know that the perceptron can separate all 8, and we can see that, if we flip the dichotomy, if we flip each +1 and -1 point, so flip the blue and the red, you get the other 4 dichotomies. Okay. And the same perceptrons will separate those other 4 dichotomies by just, flipping which side of the perceptron is +1 and which side is -1. Okay. So you can take that top picture as illustrating that, the perceptron can shatter 3 points. Okay. But now that's a thin perceptron. Okay. You can think of that line as a perceptron, as a separating hyperplane of width 0. So now let's consider the situation where I'm going to require you to fit the data with a thick hyperplane. So imagine that I don't give you this thin hyperplane, I give you a plank of wood with some width. Okay. I give you a plank of wood with some width. Okay, and the width of this plank of wood is gamma. Okay. And now you take this plank of wood to your data points and you try to separate. Okay, try to separate. In particular, let's focus on that last collection of points. Okay, so I have a data point here, a data point here, and a blue point, somewhere here. Okay. A blue point somewhere here. Now, if I look at the fattest separating hyperplane for this data, it's going to look something like this. It's going to look something like this. Some margin. And it should be clear that if I'm required to separate this data with a plank of width larger than that fattest possible, it's not going to be possible. Okay, and this is what we're showing in the bottom, set of 4 pictures. So if I consider a fat hyperplane given by that sort of yellowish thickness region, so I'm considering hyperplanes that have to be at least that thick or that thick. Okay, so the first 2 dichotomies can be separated, but then the remaining 2 cannot, because if I now try to place my fat hyperplane on to separate this data, its margin extends outside these 2 points, and we require that the data points be on either side of my fat separator. So this is an example where the thick hyperplane cannot separate those 4 dichotomies. But then you'll say to me, but this notion of VC dimension and the maximum number of dichotomies allows me to place the points wherever I want. So it's an easy fix to allow me to separate all the dichotomies, to implement all the dichotomies, to shatter a set of 3 data points by just moving the data points further apart. Okay, solution. Move data points further apart. Okay, that's a solution to allow now the thick hyperplane, to allow now the thick plank to separate the data, and so that suggests that 3 data points can be shattered. Okay, and so this notion that the fat separating hyperplanes cannot separate all the dichotomies is only going to come into effect if you are not allowed to move the data further apart. So if your input space is bounded. Okay, so fat hyperplanes cannot implement all dichotomies if you cannot move the data far apart. So what matters is how far apart can you move the data with respect to the thickness of the hyperplane you're considering. So fat hyperplanes cannot implement all dichotomies if you cannot implement all the dichotomies if the data must be close together. For example, imagine that your input space is a bounded sphere of radius r. So the data is bounded within a sphere of radius r. So, for example, data is bounded within a sphere of radius r. Okay. In which case we expect that the ratio of the radius of the data to the thickness of the hyperplane is going to play a role. So r over gamma is sort of the dimensionless parameter that's going to play a role. And indeed, theorem. So what's the VC dimension related to? The VC dimension is related to the maximum number of data points that you can shatter. Indeed, we can show that the VC dimension, dVC, i.e. the maximum number of data points that you can shatter, is less than or equal to basically this ratio squared, the sort of width, the bound on the sphere that contains the radius, so the bound, the width of the data r divided by gamma, the thickness of the hyperplane, squared. Okay. Plus 1. So the VC dimension is at most that. So in other words, if your data is bounded within a sphere of radius r, okay, and the thickness of your hyperplanes is now getting larger and larger. For example, if your thickness is bigger than r, then you basically can't separate anything. You can just implement 2 dichotomies, which is plus 1 and minus 1. Okay, plus 1, you're on one side, minus 1, you're on the other side. If you put 2 data points, they are not separated by a distance of r, so you cannot implement the plus-minus dichotomy. Okay? And so this theorem says that if your data is bounded, And then the thick hyperplanes can have a lower VC dimension, gives you a better link from E in to E out. And this is the intuition. Now, of course, we also know that, the VC dimension for hyperplanes, even if they have zero thickness, is at most D plus 1. So you can certainly take the minimum of these. So the VC dimension is at most the min of D plus 1 and D min of D and R squared over gamma squared, plus 1. So this is the theorem. And what this says is that if you have fat enough hyperplanes and your data is bounded, then your VC dimension can be very small. And observe that in that case, when your data dimension starts getting, your data is bounded and by a smaller and smaller radius, then the fatter and fatter hyperplanes can have a VC dimension that's approaching a constant independent of the dimension. Okay. So this suggests that it's possible with fat hyperplanes to get generalization even in large dimensions. Okay. Now, so this is so this has now moved towards some theoretical justification for the fat hyperplane. Okay. Now let's prove the result that's going to be of most practical use, which is to link sort of the optimal hyperplane to the cross-validation error. And it turns out that those support vectors, the vectors that, define the fatness of the hyperplane, are going to play an important role. So let's erase and talk about the fat or the optimal hyperplane, the maximum margin hyperplane, and the cross-validation error. Let's talk about the cross-validation error of the optimal, this maximum margin, this fattest separating hyperplane. And the result is going to be quite stunning, quite surprising. The miracle of the day. So the cross-validation error, ECV, for optimal, i.e. max margin / fattest separating hyperplane. Okay, what's the result we're going to prove? Okay, so the result we're going to prove is that the cross-validation error. Now remember what the cross-validation error was. Operationally, you remove a data point, you perform your learning, produce a final hypothesis on n-1 remaining data points, and test it on the left-out data point. And now you average over left-out data points. Okay. Now what and we showed when we talked about cross-validation that this cross-validation error, which we can operationally compute, is an unbiased estimate of the out-of-sample error, of the expected out-of-sample error when you learn on n-1 data points. Why n-1? Because you've left out a point, so you're only learning on n-1 data points, and the left out point is a perfectly valid, albeit high variance estimate of the test error, of the out-of-sample error for that learning on n-1 data points. So E out of n-1, so the out-of-sample error when you learn on n-1 data points is related to the cross-validation error. This is an unbiased estimate of this guy. Okay. So if we can control, if we have a handle on the cross-validation error, we have a handle on learning, on the out-of-sample error. Okay. So here's the result we're going to prove. And this is a pretty interesting, stunning result. Miracle of the day. The cross-validation error for the optimal hyperplane, for this fattest hyperplane that separates the data, is at most the number of support vectors divided by n, the number of data points. Now, let me remind you, what was the number of support vectors? So we'll do this with a picture. So you've got some data. Okay, so some blue points. Okay. And you've got some red points. Okay. And you go and you run your algorithm, your optimal algorithm, the quadratic programming algorithm that produces the fattest separating hyperplane. Okay, and maybe it produces something like this. Okay, so it's got a margin, it's got a thickness. Okay. And you can imagine, you start at this optimal separating hyperplane, grow the cushion, and it simultaneously hits, blue points and red points, and that's where the cushion has to end. Okay. So let me box these blue points and red points that it hits. Okay. Now those are what we call the support vectors. So we call these the support vectors. Okay. They are the important data points highlighted by this fattest separating hyperplane. But more importantly, okay, if you threw away all the other data, all you need to keep are these support vectors, and you will reproduce exactly the same optimal fattest separating hyperplane. So, summary, the final hypothesis, does not change if you only keep the support vectors. These data points that are on the cushion. Okay. Now, as you generate more and more data, you're going to be generating points, blue and red, and occasionally you'll generate a point that may be a support vector or maybe inside the margin, and in which case you will update the classifier. But most of the data you generate are, away from this critical region. Okay. And so what that means is that as you generate more and more data, the number of support vectors is staying approximately constant, and this n is getting bigger and bigger. And so this says that the cross-validation error, is dropping to 0 very rapidly. Okay. And, so that means that out-of-sample error is dropping to 0 very rapidly, because the in-sample error is 0. Okay. So the in-sample error is 0, so the out-of-sample error is dropping to 0 very rapidly. In-sample and out-of-sample are getting closer. Okay. And what is really stunning about this result is that, it has no explicit dependence on the dimension. So there is no explicit dependence on the dimension. Now, it is true that as you go to higher and higher dimensions, the number of support vectors might increase a little bit. Okay, but as long as it's increasing very slowly or not at all, okay, with enough data points, your cross-validation error is under control. Your E out is under control. Okay? And that's all we care about from the perspective of machine learning, from learning from data. Okay? And it's independent of the dimension. This suggests that we can go to higher and higher dimensions and perform learning as long as the number of support vectors is under control. If we have enough data and the number of support vectors is under control, our out-of-sample error is under control. So let's prove this miracle of the day, stunning result. Proof. And the proof is not hard, even though the result is quite stunning. So let's imagine that when I'm computing the cross-validation error, so I leave out a data point, I learn, and then I evaluate on the left out data point. So let's imagine I leave this data point out. Okay, so that's not a support vector. Now, this is the critical point about support vectors. That I left out a data point that's not a support vector, which means I've kept my support vectors, which means that the final hypothesis hasn't changed. In fact, I could leave out all the other data, but I'm just leaving out this guy. So my final hypothesis did not change. So when I had all the data, with this final hypothesis, I separated all the data. So that means that this final hypothesis gets this data point that I left out correct, even though I left it out, because the final hypothesis didn't change. Okay. So let's summarize that discussion. The error made on a left out data point, so X, left out, that's not, so let's call this the error, the leave one out error, because I've left out that data point. On an X that's not a support vector, is 0. For the simple reason that the final hypothesis has not changed, because it's not a support vector. And it's only the support vectors that are needed to define the final hypothesis. Okay? So the final hypothesis has not changed, and that hypothesis classifies all the data correctly. So in particular, it classifies that left out point correctly. So the error that hypothesis makes on the left out point is 0. So I've gone through that argument now twice slowly because it's an important argument. Okay? The support vectors are all you need to reproduce this final hypothesis. Okay. Now, let's look at the left out error, the leave one out error, E leave one out, on a data point that is a support vector. Okay. So supposing instead that I leave out this guy, or I leave out this guy. Now, it's possible that the final hypothesis changes. Okay. It's also possible that the new final hypothesis will get this one correct. Okay. So you may predict correctly on this left out point and incur no error, but it's also possible that it gets this guy wrong. And you'll incur a misclassification error of 1. Okay. 1 error. Okay. So in either case, the error on this support vector, the leave one out error on this support vector is either 0 or 1, so it's at most 1. Can never be bigger than 1. So it's at most 1. Okay. And so let's see what the cross-validation error is. So the cross-validation error, ECV, is equal to the sum over your data points, little n equals 1 to big N, of the leave one out error for when data point xn is left out. Okay, and we take the average. Okay. Now, the non-support vectors contribute nothing to this. So this is equal to 1 over n, the sum over the support vectors of the leave one out for the support vector, x support vector. But that is at most 1. So this is at most 1 over n, the sum over your support vectors of 1. But this just counts the support vectors. So this is equal to the number of support vectors divided by n. End of proof. That's how simple the proof is. Okay. Miracle. We have bounded the cross-validation error in terms of the number of support vectors. And okay, there's the 1 over n. That 1 over n is coming from the fact that we are averaging the leave one out errors. Okay. But this result is quite stunning. It says that, we might be able to, control the out-of-sample error, okay, even in very, very high dimensions. All it depends on is the number of support vectors. Now, in practice, we can actually compute the cross-validation error, right? We just, leave a data point out. We only need to consider the cross-validation error for the support vectors. So we run the algorithm, find the support vectors, okay, leave out each support vector one by one and see if they get classified correctly by the leave one out hypothesis. And we can actually compute this number and not get an upper bound. But the beauty of this upper bound, okay, is that it shows us what the cross-validation error can depend on. And if we have a control over the number of support vectors, the out-of-sample error is under control. More specifically, the cross-validation error is under control. Okay. So let's summarize. So what, and this is more or less the end of our discussion for justifying the fattest hyperplane. So, we have the general perceptron, the VC analysis, the sort of generalization analysis for the general perceptron. And what did we see there? The VC dimension is equal to d plus 1. So this links the in-sample error to the out-of-sample error, okay, for the general perceptron, which establishes the first step of learning, and that's fantastic. That's fantastic. Okay. It was great. Okay. And that's why the perceptron is such a good hypothesis set. But this is, dimension dependent. Okay, but that's still good. Okay. It links E into E out. Okay. Now, what are we analyzing? We're analyzing a particular algorithm, the maximum margin, the fattest hypothesis. So this general perceptron and this VC dimension and the corresponding link from E into E out applies for any algorithm, for any way of picking a perceptron that separates the data. Okay? Now we see that if you narrow your scope, if you focus on a very special way of picking the hypothesis, the final hypothesis must separate the data with maximum margin. It's the fattest separator. Okay, so the optimal separator, hyperplane. Let's call this the SVM, support vector machine, although we haven't gotten there yet. Basically what it means is it's the fattest / max margin. Okay, now it's important to realize that it's still a hyperplane, so it's still a perceptron. It's just that the specific hyperplane separator is now chosen to be the fattest. Okay. And all kinds of other interesting properties emerged. Experimentally, we saw that bias, there's no reason for bias to go up. In fact, typically bias goes down a little bit, but variance, that thing goes down a lot. And that's because, the optimal separator is this maximum margin. It's sort of a well-defined, and it's not that variable hypothesis, even if the data varies a lot. So you change all this data a lot, and you don't change this at all. So there's no variance. Okay, you change the data a lot. On the other hand, PLA or something may change a lot depending on the data. Okay, so this means that E out, remember E out is equal to bias plus variance. And so that's going to go down. Okay, so there, experimental evidence that showed why the fattest is better. And that links to regularization and all that good stuff, all those good foundations we had before. Okay, but now, then we gave the argument that, the fat separators have, a lower V, could have a lower VC dimension. So the VC dimension is at most, is at most the min of D and the radius of the data. So how bounded is the data? Radius of the data squared over thickness plus 1. Okay. Now, in high dimensions, well, technically there's a dependence on D, but as you go, if you go into higher dimension and the data is tightly bounded, okay, and you separate with fat separators, then you could have a much lower VC dimension than the general case, than D plus 1. Okay. Now, just for full disclosure, let me mention that the hypothesis set with, fat separators is not well defined until you look at the data, because what hyperplane width should we put in here? Well, we have to look at the data separate and then look at the width. So in some sense, we're defining the thickness of our hypothesis set, i.e. our hypothesis set, but when we look at the data. So a little bit more work is needed to actually link this, into the theory that links E into E out. Okay, but we're not going to go through that. Well, you can see in the text, the proof that fat separators, cannot shatter as many data points as thin separators. Okay. Now there's another step to link that to E in versus E out, because to apply it, we need to know the thickness of the hypothesis set. But let's not get into those details. The point is that, fat separators have less separating power when the data is bounded. And you can get a link from E into E out, okay, that doesn't depend on the dimension. It just depends on how bounded is the data and how thick is the separator that you're using. Okay? And so again, it suggests that we might be able to go to high dimensions and control the out of sample error, providing that the in sample error is small and the data is bounded, tightly bounded. Okay? And then we have this stunning result that the cross-validation error, E cross-validation, is at most the number of support vectors divided by n. So if n is big and the number of support vectors is under control, the out of sample error is under control. And it looks like it's not explicitly dependent on the dimension. So again, another fantastic result that suggests we might be able to have a control on the out of sample error. That's all we care about, even in high dimensions. This says that we might have a link from E into E out even in high dimensions if the data is bounded. This says we can go directly and control the out of sample error if the number of support vectors is bounded. Okay. Now, so let me emphasize that this is the general perceptron no matter how you pick the hypothesis, and these are the nice properties if you pick the hypothesis using this special property of going for the fattest. We had another algorithm which was picking a hypothesis from the perceptron hypothesis set, the hyperplane, which was the PLA. And it turns out that that's not so bad. It's not as bad as just pick as the most general case. It's possible to get a link between the cross-validation error and parameters that are not explicitly dimension dependent. So the cross-validation error for the perceptron learning algorithm is at most this guy R squared, the bound on the data, divided by n gamma squared. Where what is gamma? Gamma is the separation between the data. It is the width of the optimal separator, whatever it happens to be. And the nice thing, so you do get a bound on the cross-validation. It's not quite as nice and clean as the optimal hyperplane. Okay, but there's another nice property that the optimal hyperplane delivers to us is that we know how to find it efficiently. Okay, so the algorithm. What is the algorithm? It's a quadratic program. So it's a bounded algorithm, n-cubed algorithm. On the other hand, the perceptron learning algorithm will find a separator, it has to end. So that was a miracle theorem that we proved, or you proved in the homework. It has to end, but we don't know when. It could go for a long time. In fact, the number of iterations is proportional to R squared over gamma squared. Okay, so that's the number of iterations for the perceptron learning algorithm. Okay, so let me summarize. We have studied the fattest separating hyperplane. We have an algorithm to find it, and it has all these nice properties, so we should use it. It self-regularizes, optimally regularizes, and we can link to E out, okay, in ways that are independent of the dimension. All right. So it's a nice, theoretically justifiable, algorithmically well-behaved. We have a nice algorithm. It's a very nice algorithm. The only thing that's wrong with our analysis up to now is we have focused on the separable case. And we know that data is typically not linearly separable. Okay? So we have to handle non-separable data. Question. Okay. So let's erase, and let's now talk about how do we deal with non-separable data. Let's talk about non-separable data. And as we see on the right, there are these two kinds of non-separability. Okay, so on the left, we see that the data is essentially linear, maybe some measurement errors. And so we would like to maintain a linear separator, but tolerate error. On the right, the problem is non-linear. We need something else. We can't do it with linear. Okay. Now, for the situation on the right, we already discussed this at length when we talked about the nonlinear feature transform, when we talked way back about linear models. Well, the optimal separating hyperplane is just a linear model. So, we can use all the machinery of the nonlinear feature transform for the situation on the right. So how does that work? So you have your data, okay, you transform to your z-space, okay, and, you pick your favorite linear model algorithm to produce your linear separator, your hyperplane. Well, now our favorite algorithm is the FAT separator, the optimal maximum margin separator. Okay, so you just run your quadratic program in your, z-space instead of the PLA. Okay? And all that discussion, all the machinery of the nonlinear transform works. Seamless. Okay? When you get a test point, you transform it and use your linear separator in the z-space to classify. So we don't need to spend too much detail on that. Okay? There's no difference. It's just that the algorithm that you deploy in the z-space is this quadratic program. So we need to focus most on the situation where we want to tolerate error. Okay? And so let's develop what's called the soft margin optimal hyperplane. So the soft margin optimal hyperplane. Okay, so this suggests that what we've been discussing so far is not the soft margin optimal hyperplane. Indeed, it's called the hard margin, optimal hyperplane. So you think you've got your hyperplane, it's got a thickness, and you try to separate the data with a fat hyperplane. Okay. And it's hard margin because you have to separate the data modulo that thickness. Okay. Now, if the data is not separable, you can't separate, with the thick hyperplane, let alone with a thin hyperplane. Okay. So you have to allow the data in some sense to penetrate that thickness, that margin. And so that's what makes the margin soft. Okay. Now, in order to sort of figure out the algorithm, let's first write down the optimization problem, the quadratic program that we had for the hard margin, hyperplane. Okay, so what were we doing? We were minimizing, so we said we're going to minimize, okay, the norm of the weights, okay, subject to separating the data. Okay, that's essentially what made it the hard margin. Subject to yn w transpose xn plus b is greater or equal to 1. And this 1 being a positive number, you could have put any positive number you wanted, but we chose 1. This 1 being a positive number, this is the constraint that enforces separation. Okay, so let me show you what that looks like with some data. So let's say you have, some data, so some zeros, some blues, and some reds. Okay, and some reds. Okay. Now when you solve this quadratic program and produce the fattest separator, you will get something like this. Okay, and here's the margin. Okay, and you can imagine, we start the margin at this separator and grow the margin, and eventually it hits simultaneously these blue points and these red points, and that's necessarily going to happen for the optimal fat separator. Okay, and the sort of definition of the points that are on this margin are the ones that saturate this inequality. In fact, we argued that when you solve this problem, the minimum over n of yn w transpose xn plus b is going to equal 1. In fact, this was the definition of separability, and then it produced this optimization problem. Okay, so it means that some data points accomplish 1. Okay, for this constraint, and all the others are strictly greater than 1. Well, which are the ones that accomplish 1 are the ones that are on the cushion, that are the support vectors that prevent it from expanding. So the 1 is coming from these points, okay, the support vectors. These guys are the ones which saturate this constraint, that make it equality. Okay. Now let's look at the situation if the data is not separable. So let's put a blue 0, a blue O here. Okay. Now the data is not separable. And you can see, so for these points, this quantity is 1. For these points, it's strictly greater than 1. Okay. For these points, it's 1. For these points, it's strictly greater than 1. For this point, this is going to be less than 1. Okay. In fact, it's going to be 1 minus something. So it's penetrated this cushion. So it's going to be 1, and I'm going to put in green. Let me put in green. It's going to be 1 minus an amount by which it has penetrated the cushion. Let me call this C. Okay. And this penetration is indicating the fact that this, fat separator is not separating this data point. It has had to penetrate the cushion. So this quantity will be strictly less than 1. Okay. And so if we're going to allow non-separable data, then we should not enforce the constraint that this has to be greater equal to 1. So equal to 1 for the support vectors that are preventing the cushion from expanding. Greater than 1 for the points that are more than separated by the thick margin. And the points that are not separated by the thick separator will have less than 1. So for each point, we'll allow an amount of penetration, an amount of non-thick separation. Okay. So instead of requiring this to be greater equal to 1, we will require this to be greater equal to 1 minus Cn. And each data point is allowed to penetrate. Okay. And we will say that these data points don't penetrate. These data points also don't penetrate. Okay, it's only this data point that penetrates. So we will require that Cn be greater equal to 0. Okay. Now, how much does each data point penetrate? I don't know. I'm just allowing it. So I need to figure out how much each data point penetrates. Now, if we just solve this problem, it turns out that what you will do is you will send all the Cn's to infinity and send the weights to 0. So in other words, you'll just say, I can minimize the norm of the weights by allowing all data points to penetrate, and I'll get an infinitely wide margin. But it's useless because all the data points have infinitely penetrated. Okay. So I need to somehow penalize penetration. I don't want too much penetration. I only want penetration when it's absolutely necessary. So I can't just minimize the norm of the weights. I have to penalize, the sum of the penetrations. So I have to somehow penalize, and we'll choose to penalize the sum of the penetrations. And, the amount by which we penalize the penetrations, let's call it a constant C. Okay. And so if I solve this optimization problem, what am I doing? I'm asking for the weights and the bias that, separate the data with some thickness, but allows penetration of the cushion by a certain amount for each data point. Okay. And I've, in some sense, tried to minimize the sum of the penetrations. So you can think of the sum of the penetrations as an in-sample error. An in-sample error with respect to the fat separator. Okay. And you can see what we're doing is we're trading off the fatness of the separator with the in-sample error. The fatter I try to make my separator, the more penetration I'm going to get. Okay. And so we say that this optimization problem, when you solve it, is the soft margin optimal hyperplane optimization problem. So if we solve this, we produce the weights and the bias that in some sense gets you a fat separator with minimum sum of margin violations. These are called margin violations. And from the optimization perspective, these are called slack variables. Okay. So in this optimization, let's look at what are the variables. The variables that you have to determine are obviously the weights and the bias, but also we don't know how much each data point, violates the margin. So you have to also determine the C's. So you minimize with respect to the weights, the bias, and the C's. Okay. And minimize this optimization. Now let's compare this with some of the things that we have already seen. What are we doing? The objective that we're minimizing is, in some sense, an in-sample error plus the size of the margin. Okay, so this is in some sense inversely related to the size of the margin. And since we're minimizing, we're trying to find as large a margin subject to a small in-sample error. Okay. We saw something like this before when we did regularization. We were minimizing the in-sample error plus a penalty term. Then it was a penalty for complexity. Now this is the size of the margin, the robustness to error. So this is now just like regularization. And indeed, C plays the role of a regularization parameter. Okay. So large C means you're focusing more on the in-sample error. So you could potentially overfit more. Focus more on in-sample error. Okay. Small c means you're focusing more on the margin. You're focusing more on robustness. So small c means more robustness, more ability to tolerate measurement error, more robustness. So more regularized, small c. Less regularized, large c. If we want to put it in the language of our foundations. Okay. C goes to infinity. Okay. Means that you're exclusively focusing on the margin violations, and you'll send all the margin violations to 0, which can only be possible, when the data is separable. So this recovers the hard margin when data is separable. Okay. So this is the optimization problem that allows us to effectively run find a thickest possible separator while minimizing the sum of margin violations. And how much attention you pay to the sum of margin violations is determined by the parameter C, which we get to pick. Okay. And as we will see shortly, this plays the same role as a regularization parameter. And so it's an important parameter to pick, and it has an effect on what happens. Okay. Now, when C goes to infinity, when C goes to infinity, you recover the hard margin, and it's only possible when the data is separable. But it's still plausible that even if the data is separable, you may not want to use C goes to infinity. So you may not want to use the hard margin. Now let me give you an example of that. Okay, so let me just give you an example of that. So let's say here's your data. Okay, I'm going to draw some x's. Okay, a nice separable data, some blue O's, approved credit, nice and separable. And let's say that there's an X over here. Now, if you focus on the hard margin classifier, you have no choice. Okay, you're going to try to find the maximum margin separating hyperplane. So it's going to do something like this, and this is going to be its margin. Okay, but now if you think about this, okay, so if you look at this, and let me erase now this separator that we picked. I'm erasing this separator. Let me put back my data. 0, 0. Okay, this guy, X. Okay. Now if you look at this data, you might think, wow, this looks very weird. Maybe this person was accidentally defaulting on credit, and that's why he got a red X. Maybe he fell down a cliff or something. Okay, so should really have been given credit based on the features. Okay. Now you could go and look through the data and try to figure out which ones are misclassified, or you could say, you know what? Let me run the soft margin classifier, even though the hard margin would have worked. And the soft margin will say, you know what? I can get a huge margin by putting my hyperplane here. I can get a huge margin, and what's going to be the margin? The margin is going to be this. I can get a huge margin. Okay, but this data point has penetrated a little. For the price of a little bit of penetration, I can get a huge margin. So there can be some, and then this looks like a much more robust hyperplane. It makes an in-sample error, but we suspect when we look at this example, we suspect this might be an actual error, not an in-sample error. So this may be correct. Okay, but instead of the soft margin classifier will automatically take that into account. It'll say I can get a huge margin with a small amount of penetration. And so even though the data is separable, we may still want to use a non-infinity, a small value of C. Okay. So now let's look at some results. Okay, and here is some data. Okay, and I'm showing you the difference between C equals 1 and C equals large. C equals something like 500. Okay, and so we see that when C is small, we're focusing more. This doesn't have as large a contribution. We're focusing more on the width, and you get a wide. That's this yellow region. You get a wide. You get a very thick separator with lots of penetrations. Because when C is small, we don't care about penetration. We're focusing mostly on the thickness of the classifier. As we increase C to 500, you see the margin shrinks and there's a lot less penetration. Okay, and that's expected. That's exactly what we expect when we solve this problem with a large C. Okay, so the choice of C is important, and it trades off in-sample error with with the thickness of the hyperplane, robustness to measurement error, regularization. Okay, and here's the situation when the data is separable. Okay, just like what we just illustrated, and you can still choose, C not infinity, so you can still choose to use the soft margin hyperplane. If you choose C too small, then you can it's a situation like this, where the data is separable, but, the final classifier misclassifies this data point. Okay, and if you choose C medium, reasonably large, okay, then, you get a slightly thinner classifier, and the data gets correctly classified now. And if you choose C very, very large, you recover the hard margin classifier. Okay, and so the choice of C is important. It's an important parameter that has to be chosen. It is effectively a regularization parameter. It tells you, because what are we? We're in the game of tolerating in-sample error. Okay? And we need to precisely define what it means to tolerate the in-sample error, and that's what this parameter C quantitatively defines. What do you mean by tolerate in-sample error? Tell me explicitly, how much do I penalize margin violations? Okay. But the nice thing is that this problem, you might ask, how did I get these solutions? This problem, and now this is an exercise for you, is also a quadratic program. So this is also a quadratic program. Okay. So that's how we tolerate error. We instead of using the hard margin support vector machine, instead of using the hard margin optimal hyperplane, which is this optimization problem without the red parts, we use the soft margin optimal hyperplane. And now, when you use the soft margin optimal hyperplane, you have to pick the regularization parameter C. Okay. So let's briefly have a look at some results and discuss a little bit, the second kind of, that we showed over there, the second kind of non-separable data, the one where we have to use the nonlinear transform. Okay. Let's now talk about the coupling of the nonlinear transform with the optimal fat separator. Now, first, let's look at the nonlinear transform with our old technology, just a plain old-fashioned linear model, and and our algorithm that we will use in the Z-space is the pseudo-inverse algorithm. So we'll use linear regression for classification. Okay, so now what's our Z-space? We're doing the third order polynomial, so phi sub 3. Okay, and then the pseudo-inverse linear regression for classification, and we get our classifier in the Z-space in the third order polynomial. Okay, and then we see what that decision boundary looks like in our X space, and it's this, it separates the data as the nonlinear transform is designed to do. Okay, but it doesn't take much to convince you that there's a little bit of overfitting going on here, because you have a lot of parameters to play with in the third order polynomial feature space. Okay, and so we've overfit the data. Now, let's see what happens if I use the same Z-space, and this is very important. I'm using exactly the same Z-space. So I'm going to use the third order feature transform, but instead of the pseudo-inverse algorithm, let me get the fattest separator, the fattest hyperplane that separates in this third order feature space, okay, and then see what the corresponding decision boundary is in my original, two-dimensional features. Okay, and there you go. Wow! Okay, look. Considerably less overfitting, and it more or less reproduces the target function. And I'm showing in sort of yellow the thickness of the separator. Okay, and I've boxed the support vectors, and you will observe that in this third order feature space, you have a lot of parameters. You have a lot of degrees of freedom. All the parameters for this general third order polynomial. But effectively, what determines the separator is just these 6 support vectors. So even though you have a lot of flexibility, a lot of degrees of freedom, the separator is effectively determined by just a small number of support vectors. Okay, and you will observe another interesting thing is that we saw when we discussed the linear fattest hyperplane, the thickness of the hyperplane was the same on both sides and uniform. Well, that thickness is the same and uniform in the Z space. In the actual X space, you see that the thickness of this separator varies. Okay. But the main point here is the theory in action. Even though you have the flexibility of the third order polynomial, once you put this constraint that you're going for the fattest separator, effectively it lowers the number of degrees of freedom. The cross-validation error is related to the number of support vectors, not the number of degrees of freedom, the dimension. Now, just for comparison, I also did the transform to the second order polynomial space and used the support vector machine, the optimal fat hyperplane, and you see it's beautiful. This is basically the target function, more or less. Okay, and now we have 1, 2, 3, 4, 5 support vectors, and we have a nice yellow fat separator. Okay. And what you will observe is that in going from the second order polynomial to the third order polynomial, you've almost doubled the dimension of the space. But the number of support vectors just went from 5 to 6. Nowhere close to double. Okay? And this gives us a lot of hope that we can go to high dimensions, okay, and still get good performance like this third order polynomial versus the second order polynomial. And what's saving us? What's saving us is the robustness of the fattest separator, okay, which effectively reduces the number of degrees of freedom to the number of support vectors which control the boundary, as opposed to the number of degrees of freedom, which would result in this very complicated separator if unregularized. So the support vector machine, linear model in the nonlinear transform space, in some sense, automatically, maximally regularized. It allows us to use the complex decision boundary without suffering the penalty of all the degrees of freedom. It constrains the model significantly. Regularization at work, but in this case, automatic regularization at work. And what controls the performance is the number of support vectors. So this leads us to an interesting possibility. Can we go to even higher dimensions? Can we go way beyond the third order polynomial? Can we go, for example, to infinitely many dimensions? Wow! Imagine being able to perform, a nonlinear transform to infinitely many dimensions and then separate. Then we can separate anything. Right? But then should we be overfitting? Well, if the number of support vectors is kept under control, or if you can do this with very large margin, then you have control, large margin, because that's the DVC, is the bound is the bounded data, the tightness for the bound of the data divided by the margin squared. Right? If you can control that, or you can control the number of support vectors, then we can control E out, okay, and benefit from infinitely many dimensions. Wow! Okay, so separate the data with huge margin in large dimension. Okay, but then there's the issue of, does this really work? So will we be able to control the number of support vectors? So does it really work? And what are we talking about? Infinitely many dimensions? How do you go to infinitely many dimensions? What kind of a feature transform transforms us into an infinitely large, infinitely dimensional Z space? We're not going to be able to do that. How can we do that efficiently? We'll be, running the algorithm forever. And so the miracle of the next lecture is we're going to show you how we can efficiently go to infinite dimensions. Wow! So we can run the optimal fat separator in infinite dimensions, and we can still survive, even though we've gone to a huge dimensional space, we can still survive because the number of support vectors can be small, or the margins are huge. Okay, the regularization is maximum, and the regularization saves us, okay, and allows us to go to infinite dimensions. So we get ultimate power in some sense. Okay. And so stay tuned for next lecture. With that, checking out.